Hi everybody, in this video we're going to go through the Nearpod for identical twins. So starting off here with our warm-up, it says to determine the unknown measure. So we have three triangles. They are pretty special because they have some markings for us that will help us figure out our unknown measures. So this first one we have, note how we have three markings here on the sides telling me that this is an equilateral triangle. And an equilateral triangle is special in the sense that all three sides and three angles need to be congruent. Remembering that in your triangles, all the angles have to add up to 180. So if all of my angles have to be the same, that means they are going to be tripled in measure to get to 180 degrees. We simply divide out by my 3. And note that all equilateral triangles will have 60 degrees as their angle measures, because that is the only measure that will allow for this 180 degrees and split 3 ways. On my middle triangle, I do notice I have a right angle. And a right angle means that I have 90 degrees here. And the two side markings, only two, tell me that this is an isosceles. Now, similar to equilateral, isosceles has two congruent sides and then also two congruent angles. We'll find those angles by looking across from my congruent sides to know that these two angles have to be the same. So in this case, when I am solving for what is these missing angles, and I know that I have the 90 degrees, I can say 90 plus 2x, because these two have to be the same, equals 180 degrees. I'll subtract out my 90. 2x would equal 90, and then divide by my 2, giving me that my missing measure is 45. So this one we can kind of also note it. This is a very special triangle of 45, 45, 90, and you'll see it come up in our learning target when we view that next. My final triangle, I have 60 in all of my angle measures. So that means, again, that's telling me I have an equilateral triangle. Since all of the angles are the same, all of my sides have to be the same as well. So if my known side here is 5, that means all of my sides have to be 5. So this missing measure, this unknown measure, is 5 in this case. The next slide that you'll see in your Nearpod is looking at our learning targets and success criteria. I will pause here to go ahead and read through them. So learning targets, I will learn to prove that points on a perpendicular bisector of a line segment are exactly those equidistant from the segment's endpoints. I will learn to prove that the base angles of isosceles triangles are congruent. And I will learn to demonstrate the 30, 60, 90 triangle theorem and the 45, 45, 90 triangle theorem using algebraic reasoning. Now, we're not going to attack all of these learning targets in this single lesson. This is split up into 2 days. So today's success criteria, we are focusing on using the information about triangles to solve problems using algebraic reasoning. We are mainly going to attack the first learning target about perpendicular bisectors of a line segment and showing that they're equidistant from the segment's endpoints. So to get us started, getting us warmed up even more, we are going to review our different triangle congruences. Remember that we originally started with 3. This quarter we'll be learning about more. So we had our SSS, 3 sides have to be congruent. SAS, we have 2 sides with our included angle. And then an ASA, 2 angles with an included side. So let us take a look. Our first task here is to determine why these triangles in each pair are congruent. Okay, so let's take a look. I've got some side congruency marks on the side AC, showing that it's congruent to the side CE. And then I have congruency marks that match up for DC and BC. So I do have two sides, which means we're likely not to use the angle side angle because that would tell us that I would need two angles. Looking at here also, my diagram, something that's not marked, but something that we're allowed to assume is, notice we have this intersection point at C, creating an X with some of the angles of my triangle, leaving me with these vertical angles. So I do have one set of angles here. So let's check out our pattern. I have a side, angle, and then a side. So these triangles are congruent by an SAS. For my next set of triangles here, again, do we have an SAS, SSS, or an ASA? Let's take a look at our markings. I have AB. That side is congruent to the side CD, okay, because they have just the one mark through them. Then the side BC is congruent to the side AD with the double marks. Now remember, something that we are allowed to assume here is this shared side. It's always going to be congruent to itself. So in terms of my pattern, in terms of what I know, I'm not given any angles. So that means I'm not going to be talking about angle side angle or a side 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 or a side angle side, because again, no information about angles. So that must mean that we have a side side side, and we can see that here we have a side, side, and then a side. Lastly, these set of triangles, it looks just like the ones that we were just looking at. However, these sides have arrows on them. Okay, so remember that the arrows mean that they are parallel. Now, this is something that we kind of more freshly learned in this quarter. Arrows mean parallel versus the slashes or the dashes are just congruent. So don't mix those up. We don't know anything about these side lengths right now. What I do know is that if I have parallel lines, so let's extend these a little bit, and they are cut by a transversal, I have some angles that I can state are congruent. So in this case, I have this angle would be congruent to this angle by your alternating interior angles. Okay. Now let's take a look at our other set of parallel lines, because these are going to give us some different angles. So I have these parallel lines extending, still using AC as my transversal. I can now use this angle right here to be congruent to this angle right here, again, by alternating interior angles. Now, the last piece of information that I have from this diagram is the fact that they share the side AC. So again, we have that shared side that's going to be congruent to itself at all times. So the information that I have is that I have an angle, this side, and an angle. Okay. Hopefully, when we talked about these sides being parallel versus congruent, we should have ruled out side, 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 because then we don't really have information about all of my sides at all. In this case, we have the pattern of an ASA for my two triangles, using our alternating interior angles from my parallel lines, and then that shared side. So if you remember back to our learning target, I said that we were going to focus on the perpendicular bisector theorem, and here's where we segue. We're going to take our triangle congruences, to show our perpendicular bisector theorem. So first, starting off with remembering a bunch of our different vocabulary words and key terms, starting off with bisecting, okay? So it says, suppose that CW and SD bisect each other, which means that each of these line segments, C to D, and then C to W and S to D are cutting each other in half using P as its midpoint. Okay, that's its intersection point. And so if each of those segments are cut in half, that means CP is congruent to PW and SP is congruent to PD. So those are congruent pieces. We want to explain how we can demonstrate that these triangles are congruent. So here, I do know that I have these right angles, and we've talked before that all right angles are going to be equal to itself. That's one of our theorems. However, if I were to use that right angle as part of my proof to show that they're congruent, I'd have this pattern ASS or SSA that we never want to use. So that's not a valid congruence that we can use. However, thanks to the fact that P is this intersection point creating some X's here, I do have vertical angles. Now that I have placed that angle that is congruent, and I know it's congruent, in between my sides that I know to be congruent, I now have a pattern of SAS instead of our unwanted SSA or ASS. Now that we've reminded ourselves about some bisector things and our triangle congruences, taking a look at this diagram. This explains our perpendicular bisector theorem, which states points on a perpendicular bisector of a line segment are equidistant from the segment's endpoints. So that's a lot of words, a lot of weird combination of words that might not make sense. So let's try to make sense of that together. So starting off with this diagram, I know that I have the line AC or AB is being bisected by this line segment EF perpendicularly. And so that we know what we're talking about in terms of perpendicular bisector, that means EF crosses AB at a right angle, and it cuts AB in half such that the measure from A to C will be equal from the measure from B to C. And now it says that points on this perpendicular bisector, this line segment, for example, the point D or the point E, are equidistant from the segment's endpoints. So here to here, they're also saying that these are congruent. They're also saying that E to A, because E is on my perpendicular bisector, and then E to B, because A and B are my endpoints, those are also congruent distances or equidistant. And we can say that because of the fact that if I have congruent triangles, that means all of its parts also have to be congruent. So taking a look here, if I start off with my triangles, let's use these triangles right here. Okay. Before knowing that the side D to A and D to B were congruent, I know that because of the perpendicular bisector, that I have a right angle that's always going to be congruent to the other right angle. I have these sides, the bottom sides, because that's what a perpendicular bisector does. And then I have my shared side, D to C, as that being equal as well, or congruent. So I have triangles congruent by an SAS all the time for this perpendicular bisector theorem. That's why we can say that any other part of my triangle must also be congruent. So let's briefly talk about also the converse of the perpendicular bisector theorem. I want to just state again, the perpendicular bisector theorem states points on a perpendicular bisector of a line segment are equidistant from the segment's endpoints. Now, if we move on a couple of slides, we will see it here. So from our perpendicular bisector theorem, here is how it is stated as an if-then conditional statement. So it says, if a point lies on the perpendicular bisector of a line segment, then it is equidistant from the segment's endpoints. So remembering again, taking the first part of our theorem as my if, and then my conclusion, what it is that the theorem proved, is your then. Remembering also here that the converse is just the opposite or the backwards of our original theorem. So if we take this if then and interchange it to make the then become if and the if become then, we can state the converse of our perpendicular bisector theorem as if points on a line segment are equidistant from the segment's endpoints, then the point lies on the perpendicular bisector of a line. So just reversing our original perpendicular bisector theorem is the converse. So here, this is just our conclusion for our perpendicular bisector converse theorem, stating that we can use this theorem to prove theorems about right triangles. Okay, so because the perpendicular bisector does create right angles and it does create that side that's going to be congruent always, we're going to be seeing this being used in order to show we have congruent right triangles as well. Here now we're moving on to day 2 of my identical twins lesson. So let's get started. Here we have simplified the following square roots if possible. So it's going to be very important that you can easily do these square roots. If you have some trouble, also using a calculator is fine. One of the ones that I suggest is going to Desmos.com and using their scientific calculator. But if you don't want to use that, if you want to know how to simplify these square roots by hand, let's take a look. So we have the square root of 25. Remember that a square root kind of tells us how to break apart a number with multiplication. So let's make a tree. I know that 25 is found by doing 5 times 5. And I can't go any lower than that. It would end up being like 1 times 5. That's a little redundant, so we're just going to leave it at 5 and 5 because those are the smallest numbers that we can reduce it to. Now a square root will take out these pairs of numbers. Okay, since I have 5 and 5, that is a single pair that perfectly match each other. And so the square root of 25 is really equal to just 5 outside of the square root. Okay, so think of these looking for pairs, matching them up, and taking out that single number. Okay. Now I have the square root of 4 times the square root of 3. This tree that I can make with 4 can give me 2 and 2, but 3 doesn't really break down. We're going to leave it as square root of 3. But 4 does have a pair of 2's that we can bring out. And we get 2 times the square root of 3. Okay. The next set I do have is square root of 12. So let's break that up. I know 12 can be broken up into 6 times 2, and then 6 can be 3 times 2, and those are really our smallest numbers. Amongst these smallest numbers that I do have a pair of 2's. So I can go ahead and pull out that 2, leaving behind this 3 in my square root. Note how these two answers are the same, because when we multiply square roots like this, I am allowed to multiply them all together under one roof, 4 times 3. And 4 times 3 is equal to 12. So just noticing those patterns. Taking a look at my learning targets and success criteria again, remember how in the first half of the video, we did focus on the perpendicular bisector theorem, which means that this part of the video, we are going to be focusing on isosceles triangles and this 30, 60, 90 triangle and this 45, 45, 90 triangle. So here we are seeing the introduction of special right triangles. We're going to determine the relationship that exists among the measures of the angles and sides of a 30, 60, 90 triangle. So let's take a look here. Use what you know about the Pythagorean theorem to demonstrate the 30, 60, 90 triangle theorem algebraically. Let A represent the length of the shorter leg DB, and triangle CBD is a 30, 60, 90 triangle. Label the angle measures on the diagram. So, things that we might have forgotten. Here we have our Pythagorean theorem. The Pythagorean theorem says that a squared plus b squared equals c squared, where a and b are legs of the triangle, and c is your hypotenuse. Okay. In this sense, this can only happen on a right triangle. Here are my legs. And the diagonal that's always across from my right angle, this is always your hypotenuse. A 30, 60, 90 triangle just tells me all of the angles of my triangle. So in this case, I'll have a 90 degree. I should have a 30 somewhere and a 60 somewhere. That's how we identify this 30, 60, 90 triangle. So it says that CBD is one of them, and that DB is represented by the lowercase a as my shorter side. And I do have a 30, 60, 90. So things that I know about this triangle CBD is that this angle is going to be my 30, this one's going to be my 60. Now, I know this because when we talk about angles and their triangles, if you think about an angle that has a really small angle, I know that this length is going to be short. If I make my angle larger, right, seeing how we have a smaller versus a larger angle, I know that this length across from it is going to be longer. So that relates to my triangles and my angle measures and those side lengths, is if I have a smaller measure, so that's why I chose this to be 30, the measure of the side across from it has to be the smallest side. And it says that let A represents the shorter leg DB. So 60 is going to represent the longer leg. That's across from it over here, the CD part. And then 90 does represent the longest piece. Hypotenuse should always be your longest side of your triangle. Okay, so we have that done. So that last diagram was really checking to see how you can identify where is your A, B, and C according to your angle measures. So here we're seeing it again, much larger diagram here. Using A as my shortest side, leg, and I'll call it a leg, because it is across from my 30 degrees. It's across from my smallest angle measure. Then B does have to be another leg. It is representing the longer leg. And then C is represented by the hypotenuse. Now we're seeing a lot of other letters here. We're seeing that C equals to A, B equals A root 3, because that comes from this 30, 60, 90 triangle theorem. And it states that the length of the hypotenuse of a 30, 60, 90 triangle is 2 times the length of the shorter leg. Okay, so really, if I had a 30, 60, 90 triangle and I knew the length of my shorter leg, I can double it, and that would be the length of my hypotenuse here. And the length of the longer leg is root 3 times the length of my shorter leg. So again, if I knew my shorter leg length, I just multiply it by a square root of 3, and I know that's the length of the longer leg. The other triangle theorem that we have is the 45, 45, 90 triangle. So this is another special one where my angle measures, the 45 and 45, are going to be equal. So that means, in terms of looking at my side lengths, since the angle measures are equal, the legs should also be equal. Okay, so noticing if I had either the side length or the leg of A or the leg of B, it should be the same as the other leg. However, it states that the hypotenuse of our 45, 45, 90 triangle is going to be a square root times the length of a leg. Okay, so that's our 2 triangle theorems. We're going to look at some practice. So starting with my 30, 60, 90 triangle, I have a given here that my short leg, so this is A, is 5 units long. That means this X here, this unknown X, is my longer leg, and it should be my short leg, A, times the square root of 3. And then my hypotenuse, again, always across from my right angle, this is going to equal 2 times my value of A. So since I know that my short leg is 5 units long, that means my longer leg should be 5 times the square root of 3. And then my hypotenuse is 2 times A, or 2 times 5, which I know is to be 10. Okay, hopefully not too bad there. Taking a look at another 30, 60, 90 triangle. This time I gave you a different piece of information. This time, this unknown X is my shorter leg of A. And I don't know it, but I do have my longer leg, which is supposed to be A times the square root of 3. So taking away from this pattern, I've got 7 root 3 as my known information. And what I need to know is A. So A must be this 7 that's attached to my square root of 3. So my shorter leg is just 7. And then my hypotenuse across from my right angle, this is going to be the value of 2a, 2 times my shorter leg. So I've got 2 times 7, which is 14. Now taking a look at one of our 45, 45, 90 triangles. So remember that my two legs are always going to be equal to each other. So if I have the measurement of one leg, it should be the same as the measure of the other leg. So this is also equal to 9 units. And then my hypotenuse, that's again always across from my right angle. In this case, it's going to be my leg value. So I'm going to say A times the square root of 2. My leg value is 9. So this is 9 square root 2 for my hypotenuse. This one, again, another 45, 45, 90 triangle, but I gave you the information for the hypotenuse instead. Remember that this hypotenuse is still always the length of your leg times the square root of 2. So if we take a look at our patterns, I have my square root 2 attached to this 12. So this 12 must be my leg length. So both my legs are the length of 12. For the rest of the lesson, you're going to see more examples and being able to practice finding the side lengths for your 30, 60, 90 and your 45, 45, 90 triangle. So I will end on this worked example where you can see the work for solving our different side lengths on our two different triangles. Remembering that if we are multiplying square roots of the same square root, then we can always combine them together under this one roof. Okay? And then also remembering how to separate them when we see those pairs of the same number that can come outside of my square root. And then on the right side, this is something called rationalizing our denominator. It is a skill that is nice to have, but we won't require you to do that here in geometry for now.